Welcome to Brain Vision.
In this question, there are four forces acting on the picture. The weight force, the force that's being used to press it against the wall, the normal force exerted by the wall as a response to the force that is pressing the picture against the wall, and the frictional force that holds the picture in place. Then we have to calculate what is the minimum amount of that pressing force F to keep the picture in place. Then we have to use Newton's second law to solve this question. We have to use it in two different axes. So we have to use it on the vertical axis and in this outside pointing axis. Let me call this axis Y and this axis X. And let me choose it to be such that everything that is pointing outside the wall is positive and everything that is pointing up is positive too. Then we apply Newton's second law on each of those axes. So for the vertical axis we have the following. The net force acting on the vertical axis is equal to the mass of the picture times the acceleration of the picture in the vertical axis. We want the picture to be standing still. We want it not to move, and it's not moving previously. Therefore, its acceleration is equal to 0. Then the net force in the y direction must be equal to 0. But the net force on the y direction is composed by two forces. The frictional force that is pointing up and therefore is positive in our reference frame, and the weight force which is pointing downward, so it's negative in our reference frame, and this is equal to 0. So as a consequence, the frictional force must be equal to the weight force, and this is our first conclusion. So the frictional force must be equal to the weight force. But the frictional force is given by the following expression. In this situation where the object isn't moving, it's equals to the static frictional coefficient times the normal force that is acting on it, and this is equal to the weight force. Then we conclude that the normal force that is acting on the picture must be equal to the weight force divided by the static frictional coefficient. Now we apply Newton's second law on the other axis to get more information. So the net force on that other axis is equal to the mass times the acceleration in that other direction. Again, we want the picture not to move in this direction too, so the acceleration is equal to 0 again. Then the net force on that direction is equal to 0. But the net force in this direction is given by two forces. The force that is pressing the picture against the wall and the normal force. The normal force is pointing outside the wall, therefore it's positive, and the force that is pressing the picture against the wall is pointing to the inside, then it's negative, and this is equal to 0. Therefore, we get a relation between the normal force and the force that is pressing the picture against the wall. But we have already a relation between the normal force, the weight force, and the static frictional coefficient. And this is the normal force that must be acting on that picture to hold it in place. Therefore, the force F that must be pressing the picture to keep it in place must be equal to the weight force divided by the static frictional coefficient. Then, remember that the weight force is given by the mass of the picture times the acceleration of gravity, and this is divided by the static frictional coefficient. Also remember that the acceleration of gravity near the surface of the Earth is approximately 9.8 meters per second squared. Then, substituting the values that were given by the problem, we get 1.1 times 9.8 divided by 0.66 is equals to the minimum amount of force that must be applied in the picture to hold it in place. And this gives us a minimum force of approximately 16.3 newtons. And this is the answer to the question.